molecules that obviously have been with us for a very, very long period of time, but are really fascinating molecules. Okay? In the category of drugs also, they are really fascinating, and I did introduce to you a little bit about heparins as drugs and the key components. Given that some of you attended my lecture on anticoagulants and heparins, I think you'll see that some of it is repeat, but this particular lecture goes a little bit beyond what I did this in the anticoagulant lecture. And the key aspect of what I want to do today is tell you a little bit about heparin as a background, but also introduce to you low molecular weight heparins in way more detail than what you have seen so far. Both unfractionated heparin and low molecular weight heparins are really, really important drugs, and it is extremely interesting that now we have generic low molecular weight heparins too. Okay, and I think that development essentially puts this entire field into kind of a new perspective. And in order for you to understand as to what are the implications of having generic low molecular weight heparins, I would like to discuss the topic of biosimilarity. So this hopefully will tune you in the direction of glycosaminoglycans as drugs and the challenges and the opportunities both in the field. Okay, so this is the outline in slightly more detail, but let's begin with heparin. So heparin has been with us for a very, very long period of time. Heparin was discovered in 1916, very close by at Johns Hopkins University, and they were actually trying to discover coagulants, and they discovered an anticoagulant, right? Which is pretty interesting. You would think that a molecule that is essentially present a lot in our body would be the first one to be discovered. But, well, it was 1916 and somebody came up with something that was highly soluble in water and kind of unusual, and they identified heparin. Okay, well, even at that time, it wasn't really known as to what is the structure of heparin. And close to 8 years passed before one component of heparin was identified as a constituent, and that was uronic acid. Okay? So uronic acid, 8 years to simply say uronic acid is one of the constituents of heparin. Then another 8 years to identify glucosamine, the second component of heparin. Right? So these days, when you make molecules, you kind of come to know of structure fairly easily. But this was the state back when, close to 100 years ago. And then it was identified that heparin was sulfated after about 5 more years. Okay. It so happened that because they were looking for coagulants, that they had some idea about what the activity was going to be, because they discovered an anticoagulant, that they thought of immediately doing studies in animals. And it was found that the molecule is very effective as an anticoagulant. And this was preceding the FDA days. So it was easy to get something that works in animals, something that works in humans, without much characterization, approved and introduced into the clinic. Right? Now, of course, that would not really be the case. So even here, the structure was not really fully identified. How many components do we know of for heparin? Just about 3 components. It has a uronic acid, it has a glucosamine, and it is sulfate. That was the structural characterization of a molecule that has reached people and is being introduced, injected into human beings at that point. Was anything known about the mechanism of how it works? No idea. Look, in 1973, close to 30 years after it was being used, was the mechanism of how the molecule works discovered at MIT. And Bob Rosenberg found that heparin binds to a protein in our body called antithrombin. And antithrombin is an anticoagulant protein. Antithrombin is a protein that we all have, without which we cannot survive, and is a molecule that basically generates the anticoagulant action. Even at this point, the structure of heparin was not known. The structure had been identified to be these three components, and then they had identified variations of these structures and things of that sort, but the full structure was not identified. Then pretty much after this, it was identified based on reducing the length, the chain length of the molecule from close to 50 to close to 8 or so, that they started investigating the structure of an octasaccharide, from which they identified a pentasaccharide as the key structure that is responsible for binding to antithrombin. And this was done in the lab of Bob Rosenberg as well as Ulf Lindahl in Sweden. And both of these are now stalwarts. Both of these are alive. And Ulf Lindahl is even today associated with the paper once in a while. But they are highly recognized for discovering the mechanism of how heparin works. And the key sequence of pentasaccharide that is involved in binding to antithrombin. This particular sequence we will discuss in just a little while. Yeah.
How did they find out those three components? How did they know that those are essential?
So the uronic acid and the glucosamine. So back in the olden days, there was no kind of NMR. There was no mass spec. And what they used to do was they would chop it down chemically, which is acidic hydrolysis. And then when you do acidic hydrolysis, all the sulfate groups are lost. So that is the reason they did not know that there was sulfation, and it took so long to discover the sulfate. But basically they would hydrolyze it, then they would chop it down, that is also acidic hydrolysis. And then they would modify it by acetylation, by methylation. And then they convert it into a neutral unit. Could be disaccharide, could be monosaccharide. And then they would have the standards. So they would do TLC, and then that's how they would do one at a time. So this was simply brute force TLC, and I'm pretty sure they must have done HPLC and things of that sort. And back in the olden days, it used to be elemental analysis. So they would do elemental analysis, and then they would find it. Okay. Now, as you probably know, heparin is a mixture of millions of species. The average molecular weight of a heparin chain is about 13,000 or 15,000. Because it's not all chains have the same length. Some of the chains are disaccharide, some of the chains are tetrasaccharide, hexasaccharide, octa. They're also odd numbered chains. And some of the chains can actually go to 100 monomers. That we have to say that it is polydispersed. What does that mean? It simply means that there are chains of different lengths. Okay? And because it is a heterogeneous and polydispersed molecule, we define two types of molecular weights. Those are weight average molecular weight, MW, and number average molecular weight. Okay. Weight average molecular weight and number average molecular weight. I'll give you a simple physical explanation of why do we have to define in this fashion. So, if we consider that we are 4 or 5 people here, and all of us essentially have the same weight, let's imagine 200 pounds. None of us is 200 pounds, but let's imagine 200 pounds, right? Then we calculate the total, 200 plus 200 plus 200 plus 200 divided by the total number of people in the room. That's called the average molecular weight. But if all of us have the same weight, then that will essentially be 200, right? So that is called the number average. We are simply taking the total weight divided by the number of people and finding an average. That's called the number average molecular weight. But we know that we are all people of different weights. Okay? In a large population, such as Richmond, okay, people have different weights. But then, is the number going to be equivalent for the entire population? Is the number average molecular weight going to be equal for the entire population? No, because people have different weights. But then some cities might have very fat people, and some cities, there might not be enough food available, so they might have really, really skinny people. So how do you compare these kinds of cities? We compare these kinds of cities by the number, weight average molecular weight, or weight average weight, for comparison of weights of people. So that takes into account how many people are skewed, what is the distribution that is skewed on the higher molecular weight or lower molecular weight or average molecular weight size. So the weight average molecular weight gives you the distribution of weight. In terms of molecules, in terms of chain lengths, the weight average essentially says how, if you have a sample, does this sample have more longer chains or more shorter chains? Because the chain length is different. Okay. And so what this means is that 30%, 1.3 to 1.4, 30 to 40% of chains are on the longer side. If all chains were of equal length, we would get a number 1. Polydispersity would be 1. That's true for homogeneous molecules. All homogeneous molecules have a polydispersity of 1.0. Here, the chain lengths are different, and therefore, we have a polydispersity higher than 1. Got it? Is that clear? Yeah? The average chain length is approximately 40 to 50 monomers. Okay. And so, you really have to think about disaccharides. So there are close to 20 to 25 disaccharides in an average chain of heparin. That's what it means. 20 to 25 disaccharides. Amongst these disaccharides, you can have disaccharides with varying levels of sulfation. Very quickly, this is the structure of heparin. Okay? This is the structure of heparin. And as you can see, that this is an unending sequence here. What is shown is an unending sequence. But basically, you have a repeating unit of glucosamine and uronic acid, which repeats. And that's the building block. The repeating unit essentially can have variations at the 6th position of the glucosamine, or at the 2 position of the glucosamine, or at the 2 position of uronic acid, or at the 3 position of glucosamine. And because of these variations, and the uronic acid itself can be of the iuronic acid type or the glucuronic acid type. And because of these variations, you can have multiple types of disaccharides. And when you have multiple types of disaccharides, the proportions of these disaccharides are going to change. The highest proportion is of the trisulfated disaccharide. Okay? Glucosamine 2S, 6S, iuronic acid 2S. So it is this particular disaccharide that is present here. Well, that is not present here because this is the pentasaccharide. The pentasaccharide has none of that. But if this was sulfate, and if this was sulfate, if all 2 X's and 1 Y were sulfate, that would be the common disaccharide, which is the glucosamine NS6S iodonic acid 2S. In a chain of heparin, not in a chain, but in 1/3 of chains of heparin. So not all chains of heparin would have the pentasaccharide. Only in 1/3 of the chains would you get this kind of a sequence, which is called the antithrombin binding pentasaccharide sequence. This particular chain sequence, or the pentasaccharide sequence, has a glucosamine carrying 6-sulfate, a glucuronic acid carrying, this is also not correct. This should be OH. Glucosamine, which doesn't carry any 6-sulfate. Then you have a glucosamine carrying N-sulfate and 3-sulfate. Then you have an iodonic acid carrying 2-sulfate and a glucosamine carrying N-sulfate. Okay, so that's the structure of the antithrombin binding pentasaccharide. This is a mistake. This should be OH. And this is the sequence that recognizes the antithrombin residue, antithrombin protein with very high affinity. This is the reason why heparin is an anticoagulant. Okay? This sequence is present in only 1/3 of the chain. So it's about 1/3 of the chain. 25 to 30% of chains have this sequence. So once again, not all chains have this sequence. Only about 1/3 of the chains have the sequence. So if you think about this, heparin is a drug. You can imagine that this particular molecule, what proportion of the molecule is actually a drug? Only 1/3 of the proportion, right? So it's a very fascinating molecule from the perspective of drugs. All right. Now, so heparin is still used today, right? Heparin is still used today. Heparin is used essentially as unfractionated heparin. So when we say heparin as anticoagulant, and when we have heparin being injected in clinic, that heparin is actually called unfractionated. The technical name is unfractionated heparin. Heparin cannot be synthesized, has not really been synthesized as yet. I forgot to mention that although I'm showing you the structure here, this was discovered in 1916, right? This was discovered in 1916. And we now know fairly well the structure of heparin. But if you say, I have a chain of heparin, what is the structure of that chain? We still don't know. Okay? Even today, we still don't have technology to say that this is the structure of heparin. What is shown here is a representation or an average representation of a sample of heparin. That's what it is. Okay? So although we typically say this is the structure of heparin, that's really not really true at all. Okay. So heparin cannot be synthesized. Heparin has to be isolated from animal sources. So back about 20, 30 years ago, heparin used to be obtained from several animals, from dogs, from cow, from pig, the one that is used in the clinic. These days, heparin from pigs is the only one that has been approved for clinical use. We cannot have heparin from dogs. We cannot have heparin from pigs or from cows. The only one that we use is from pigs. It turns out that heparin from dog and from cow and from pigs are different. The anticoagulant activity of cow heparin is different from that of dog heparin. By the way, we also have a heparin. Our heparin is fairly similar to these animals, but it's reasonably different too. Okay, so it's not identical. Yeah.
There have been studies comparing efficacy between different animals heparin compared to also human heparin.
That's correct. So there have been studies that have been done, efficacy studies as well as structural studies, have been done on heparins from different species. Not only that, heparin can be obtained. Notice the organs for isolation of heparin are different. Dog is liver, cow is lung, and pig is intestine. Okay, so they are not the same organs. It turns out that heparins from these different organs are actually different. In fact, our heparin, if you take liver heparin from lung heparin, there are microscopic differences. So it is not that the heparin is same across our entire body. Heparin is actually different. Heparin is therefore not only different in different species, but it's also different from different tissues. Okay? You have to realize the implications of this. Okay? You have to realize the implications of this. All right, before I talk about implications, let's just go through the process of how heparin is isolated. Okay. Once again, this cannot be synthesized, and heparin is actually a very complex molecule. Right? Millions of species generate the sample of heparin that we typically use. Nature provides us that kind of a mixture. So the basic steps that are involved in the preparation of heparin, which eventually go into the formation of the unfractionated heparin for clinical use, is first of all tissue preparation. An appropriate form of tissue has to be prepared. Then you use heparin extraction. Then you recover a heparin called stage 12 heparin. And then obviously you purify heparin. Heparin that, for example, the United States imports from China today is stage 12 heparin. The United States does not make heparin from scratch or does not isolate heparin from pigs. The United States basically imports all of its heparin from stage 12, the stage 12 level, and then processes it. Okay, so what are the 12 steps? Stage 12 heparin essentially are 12 steps. 12 steps of heparin preparation. Now, heparin is obtained from pigs, and pigs' intestine, the intestinal mucosa actually. So this is that part which nobody eats, and is basically thrown away. So this is obtained from slaughterhouses. It is basically collected from slaughterhouses, and after you collect all of that from slaughterhouses, you basically chop it, enhance the surface area, and then you treat it with sodium hydroxide at a slightly elevated temperature and pressure. Okay? So at this point, whatever that you collect is kind of yellow, brown kind of mass, and it has lots of proteins and other stuff which you want to remove heparin from. So alkaline hydrolysis releases heparin from its proteoglycan form. And then you remove the proteins that are basically present in that mix. You chop it down into smaller species. Then there might be some particles in it, so you filter it. And at this point, whatever that is filtered actually contains glycosaminoglycans, which is heparin is one of the glycosaminoglycans. And there are peptides, and there might be nucleic acids. At this point, enzyme inactivation, if there are enzymes in it, which is one of the few enzymes that are added at this point, they are inactivated by high temperature, cooking at high temperature. And then that is basically absorbed onto an anion exchange resin. Heparin is highly negatively charged. That's the beauty about this molecule. Heparin is highly negatively charged, so it's absorbed onto an anion exchange resin. And then the unbound material, or loosely bound material, which is not really heparin, can be washed by an appropriate salt wash. And you elute with high salt fraction. Heparin is tightly bound, and that interaction can be disrupted, tightly bound to the resin, and that interaction can be disrupted at with high concentration of sodium chloride, and it's filtered. At this point in the solution, you essentially have majority of heparin, but it's in water. Okay? So what do? You precipitate that heparin with ethanol. Remember, we are thinking about heparin that is required for a large number of patients. Practically, I would say 100 million patients take heparin every year in the United States alone. Okay? So we are really talking about tons of quantities of heparin. So for that, we can't really have very sophisticated method of preparation. Otherwise, that will make heparin very, very expensive. And heparin is obtained from essentially trash material, unfractionated heparin. So we come up with some very simple methods. Actually, anion exchange resin is also a fairly sophisticated technique to generate heparin. So the simple method is precipitation with ethanol. So what is this technique? This technique is that heparin is present in water at high concentration. As you keep adding ethanol to it, you are essentially changing the solubility of heparin because it is no longer now water. Heparin is insoluble in ethanol. Heparin is highly soluble in water. And as you keep increasing the ethanol concentration, proportion, not concentration, proportion, you're going to make the heparin less and less soluble. So what happens is that at this point, you have heparin and you have high salt in water. Okay? And it is highly sulfated. So higher the sulfation level, lower the solubility in ethanol. So as you keep increasing the concentration of ethanol, higher sulfated heparins start precipitating out first. Okay? And in this fashion, you can actually do fractional separation. Theoretically, you can do fractional separation. So that precipitated heparin, a certain proportion is collected. You can actually reach levels of 90% ethanol, 10% water. And you can get all of heparin come out of that solution. Now, after you prepare, this is clear? After you prepare this, you can then do vacuum drying to really generate a solid cake, which is called stage 12 heparin. That's the stage 12 heparin. Without any sophisticated purification. This is stage 12 heparin. It cannot be injected in humans at the present time. Right? But basically at this point, heparin can be sold. Stage 12 heparin can be sold. And so there are these slaughterhouses in China. They basically collect this and they cook this up on site. And they sell it to companies such as Baxter. And then Baxter, for example, purchases it and it starts to manufacture unfractionated heparin that it actually goes into human beings. The purification and followed by final preparation is essentially very simple. It undergoes several steps. Dissolve the stage 12 heparin, and then you might actually have a little bit of color at this point because there are contaminants that are present. Okay? Those contaminants can be oxidized, and then you can remove some of the cations. So when you are doing all of this, when you've exposed it to lots of different surfaces, such as aluminum, such as iron, because these are done in these vessels that are not really, absolutely glass-lined vessels that are typically used for organic drugs, that you might actually pick up a number of cations. So then you do cation exchange. So you convert all cations. You might have calcium, you might have magnesium, you might have something else. And so you convert all of those into sodium, if you want sodium heparin. And then you do another ethanol precipitation and reprecipitation to generate a final heparin. So this is the process for purification of unfractionated heparin. Even at this point, heparin is still a mixture. Heparin is still a tremendously bad mixture, where only 1/3 of the chains actually have the heparin antithrombin binding pentasaccharide. At this stage, you test for its activity, and you adjust the activity against a standard, and you come to know, and then you say, this is the amount that you need to inject. So, a number of times, let's see what the next slide is. Okay. So, a number of times, you might have, in one preparation, you might have 1 milligram heparin giving activity X. But in another preparation, you might actually have only 0.5 milligram giving you activity X. There's a lot of variation. One manufacturer might ask you to use 1 milligram heparin to give you 100 international units. Another manufacturer might ask you to use 1.5 milligrams of heparin to give you the same international units. Why is that? Because the amount of the heparin pentasaccharide in the chains of heparin might be different between different manufacturers. Right? Okay, any questions here? Yeah.
If we took the tissue preparation step and we artificially made the tissue ourselves, like we produced cultures of the same pig intestine or even dog liver or whatever, would we still get heparin at the end of it? And in what quantity?
So cells.
Yeah.
So it turns out that the cellular expression of heparin has not succeeded as yet. They're still working a whole lot on generating recombinant heparin. Okay. There's a company in California that is trying to do it, but it hasn't succeeded as yet.
So does that mean we know like the genes responsible for expressing?
Right. I think you have seen a lecture, right? An entire lecture on heparin biosynthesis. Dr. Balagurunathan gave you that entire lecture. Right. NDST, 6OST, 3OST, 2OST, all of that lecture. Okay. I hope you don't forget it. Okay. But yes, we know quite a bit about the biosynthesis of heparin. Heparin is a proteoglycan from which glycosaminoglycan heparin is obtained. And so, I don't know whether you all realize the challenges, the difficulty. So if, for example, you had, okay, so if, for example, you had heparins from different tissues generate different structure and different activity. What does that mean? Can we control people in other countries, especially China, where should they get heparin from? We cannot, because we have no idea. One day, you might actually get heparin from the lung of a pig. Another day, you might actually get from the intestine. Can we say, you want only intestine? We can say that, but we cannot really guarantee it. So therefore, in terms of drugs, think about, this is a molecule that is sold at close to 500 million doses a year and has a structure which is very complex, very uncertain, difficult to monitor in terms of quality control. This is extremely difficult to monitor. And yet, we typically have very little idea, even at this point, what we are actually injecting, other than the in vitro biological activity or anticoagulant activity that could be done. Okay? So that's what the heparin is being used even today, after 100 years of its introduction. And we still cannot get away from it. We still cannot really say, I don't want to use heparin. Okay? All right. Now, heparin is an anticoagulant. It binds to antithrombin. It generates, it activates antithrombin. And this leads to inhibition of clot formation. Okay? We're going to see this in just a little while. But heparin can also do a whole lot of other things. For example, it can actually do cellular proliferation. Okay? It can bind to growth factors and induce cell growth. At the same time, it can bind to growth factors and inhibit cell growth. Okay? It can do both things. It can help cells grow, and it can also inhibit cell growth. In wound healing, it can modulate inflammation. It can reduce inflammation. It can improve wound healing. In viral invasion, there are glycoproteins that recognize heparin-like species, and therefore it could actually modulate viral infection of cells. And there are numerous other effects that are that we are not listing here. But this is one of the papers. This is a very, very old paper that you can read about all the different effects of heparin. Let's talk a little bit about coagulation. So, coagulation is a field which is fairly complex. Eventually, the coagulation cascade generates clot. And this happens through several different enzymes that are organized essentially in a cascade manner so that you get clot. Some of the enzymes in this coagulation cascade, such as thrombin, factor 2A, or factor 10A, or factor 9A, are regulated by a protein that is present in the plasma and is freely floating called antithrombin. We all have antithrombin. And this is an endogenous inhibitor of clotting. So we already have a molecule that prevents clotting, an anticoagulant molecule that prevents clotting. And it turns out that heparin binds to antithrombin to give you this kind of a complex. So antithrombin by alone itself is an anticoagulant, but it's not a very powerful anticoagulant. It's a weak anticoagulant. So what heparin does is it activates the antithrombin to inhibit thrombin, factor 10A, and factor 9A much more efficiently, so that heparin behaves as an anticoagulant. So one of the ways to visualize this and to see the magnitude of the activation is this particular slide. So this is the fundamental reaction of how antithrombin inhibits the target enzyme. By E, I simply mean target enzyme. That could be either thrombin, or it could be factor 10A, or it could be factor 9A. Factor 9A is not shown here. But basically what antithrombin does is antithrombin reacts with the enzyme and it generates antithrombin enzyme complex and covalently inhibits the enzyme. So that now the enzyme is not able to do its normal function, which is the clot formation function. Antithrombin alone has a second order rate constant of approximately 10,000. So it's kind of weak. It's not very strong. But when you add heparin to it, the antithrombin heparin complex, which is this complex, inhibits thrombin with a rate constant of 10 million molar inverse centimeters. So there is an increase in the rate of reaction by approximately 1,000-fold. That 1,000-fold increase is the reason why heparin serves as an anticoagulant. It's essentially an instantaneous reaction. So when somebody is having stroke, somebody is having pain on the left side and is about to get an attack on coronary artery, then if you come to know of it fairly fast, you would actually inject heparin, and that would prevent the clot to definitely not expand further, but also might actually reduce the possibility of damage to the heart muscles. So, same thing happens with factor 10A, approximately 500-fold increase in the rate of reaction. And for factor 9A, it's approximately 1,000,000-fold increase in the rate of reaction from antithrombin alone. So therefore, heparin makes antithrombin a better inhibitor of each of these enzymes that generate thrombin. In that fashion, heparin becomes a very, very powerful anticoagulant. Okay, any questions here? All right. So how does that happen? That happens because antithrombin, because the pentasaccharide that is present in heparin, as imagined here, this is a 5-residue sequence. This is 1, 2, 3, 4, and 5. So this is 5-residue sequence binds in a region which is defined by helix D, helix A, and a new helix P is formed in antithrombin. The enzyme that antithrombin reacts with, thrombin, factor 10A, these enzymes recognize this reactive center loop, and heparin binds, and it basically changes the conformation of this reactive center loop so that the enzymes are better recognized. This is the zoomed in version of the process, and basically the crystal structure has been reported in this particular journal some time ago, and that essentially gave us the exact mechanism of how heparin activates. What heparin does is, it binds into the active site, changes the conformation of the reactive center loop, and therefore recognizes the enzyme, especially factor 10A, much, much better. Okay, so this is an allostatic effect. This is an allostatic effect. It turns out that the allostatic effect alone is not the only reason how heparin works. Okay? And that's the interesting part. Heparin is a fairly long molecule. Okay? The allostatic effect is generated by the pentasaccharide, just a small unit within heparin. So what does the rest of the stuff do? The rest of the chain is actually also involved in recognizing certain proteins or certain enzymes. So once again, I'm giving you a cartoon as to how heparin works as an anticoagulant. And there are two major mechanisms that come into play. So this is heparin. This is the pentasaccharide sequence, DEFGH or H5 sequence. This sequence binds to the heparin binding site of antithrombin, and the reactive center loop undergoes a conformational change, okay, in the complex. Now this conformational change is better recognized by factor 10A. And antithrombin reacts with factor 10A, it inhibits it. Okay? However, for thrombin, the conformational change is not that critical because the active site of thrombin is much bigger than the active site of factor 10A. So what happens in thrombin is, thrombin also has an exosite which is positively charged. And this exosite recognizes the negative charges on the extended chain. And therefore, heparin brings thrombin and antithrombin in three-dimensional space, close to each other. And thereby, thrombin gets inhibited. Okay. So this mechanism is called the conformational activation mechanism. This mechanism is called the bridging mechanism. Okay. So although we might think that thrombin is very similar to factor 10A, is also very similar to factor 9A, but the mechanisms are completely different. And nature has engineered it in this fashion. Okay. You got it? Yeah? So, once again, you can imagine how this might be working. I'll give you a simple analogy. So, if, for example, this is the chain of heparin, right? Here's the pentasaccharide, and let's say antithrombin is bound here, then thrombin can be bound anywhere here. And then thrombin simply walks on the chain of heparin to reach antithrombin. Okay, thrombin walks on the chain of heparin. I have a simulation in just a little while to reach antithrombin, and that's how the mechanism works. So there are two mechanisms at play: conformational activation mechanism and bridging mechanism. And you're going to find that glycosaminoglycans, the way they work in biology, it is a lot of bridging, and once in a while, it is about conformational activation. Okay? With factor 9A, you have both conformational activation as well as bridging playing a role. So this is approximately 500-fold activation. This is approximately 1,000-fold activation. Therefore, this is a 1,000,000-fold activation. Got it? Therefore, this turns out to be a 1,000,000-fold activation. This is actually being demonstrated by crystal structure, published some time ago, where it shows that the pentasaccharide binds antithrombin, a trisaccharide binds thrombin, and the heparin chain actually bridges the two together. It helps them bridge the two together. And this kind of a mechanism has now also been shown, and when Dr. Patel was lecturing, he showed you FGFR1 receptor complex, and there was this kind of a bridging between the receptor and the growth factor. Same phenomena is going on. Of course, the sequence was different. So here is what is going on with regard to the bridging. This is antithrombin. Okay? Antithrombin binds to a chain of heparin at the pentasaccharide site. Thrombin binds anywhere along the chain, and then gradually it walks to antithrombin. Okay? Now, imagine what might happen if thrombin is binding to the chain in an opposite fashion. Then it would be a non-productive interaction. You realize that? So this is the orientation, because thrombin also has to have orientation. So without appropriate orientation, you're not going to find enhanced reaction. Okay? It turns out that the heparin antithrombin complex is able to inhibit not just the three enzymes that I told you about: thrombin, factor 10A, and factor 9A. Okay? The heparin antithrombin complex can actually also inhibit factor 11A, factor 12A, factor 7A, and so many other species. Okay? So it has lots of different activities. And notice that as you change the chain length, so the blue is pentasaccharide alone, H26 is low molecular weight heparin. We're going to discuss low molecular weight heparin in just a little while. H50 is the unfractionated heparin. So this is chain length variation. You can clearly see that for thrombin, pentasaccharide is inactive. If you have pentasaccharide alone, it doesn't work. H26 is 21,000-fold enhancement, and H50 is 3,400-fold enhancement. Longer the chain, higher the enhancement. For factor 10A, pentasaccharide is quite effective, 300-fold. H50 is about 1,600-fold. So the difference is not as high as what you find for thrombin. And likewise for factor 9A and for others. This is how it was discovered that the mechanisms are different. Go ahead.
When we were in advanced mechem, you showed us fondaparinx. That is only like a pentasaccharide. So how is that so active, and how is that?
Right. So fondaparinx is active because this is what is actually happening. Here, you only need fondaparinx because fondaparinx is recognized. The chain is not useful at all. Not that it's not useful, it doesn't contribute a whole lot. So therefore, fondaparinux targets factor 10A primarily. Unfractionated heparin targets thrombin primarily. So we might think that fondaparinux is same as unfractionated heparin, but that is not really the case, right? That is not really the case. There are final points about targeting. Okay, so let's do this. What time is it?
3:15.
So we have completed the mechanism part, okay? And the mechanism part directly ties into what problems we have with the heparin therapy. You can clearly see from the mechanism itself that heparin is targeting a number of different enzymes. Right? It's not that the heparin is basically targeting just 3 enzymes. Heparin is targeting these enzymes, and by the very nature, heparin targets a whole lot of proteins in our plasma. Okay? Practically any protein that has a negative charge, or practically any protein on cells that have a negative charge can actually bind to heparin. So by heparin, I mean the red box here. Okay? And because heparin interacts with so many proteins in our plasma and number of cells in blood, that you actually have a number of different systems that are being modulated. So heparin suffers from a whole lot of negative adverse consequences. Amongst these, there are few that are basically obvious and extremely important to consider for clinicians who are basically using heparin. One of those is heparin-induced thrombocytopenia. A large number of patients that are treated with unfractionated heparin suffer from this, close to 3.5% of patients. So you can imagine if 100 million people are being treated with heparin every year, we are really talking about 350,000, 3.5 million people that are suffering from heparin-induced thrombocytopenia. Okay? And that's quite a huge number. Likewise, there are people who are resistant to heparin. Quite a lot of people might be resistant to heparin. Another problem with heparin is not able to inhibit factor 10A. I just made a statement to you that heparin targets factor 10A. But heparin targets factor 10A in plasma, and factor 10A is free. But factor 10A can also be part of the prothrombinase complex. So this is a complex that is extremely important in forming a clot. Okay, I didn't elaborate on what is a prothrombinase complex, but basically it is the last major complex that generates the clot. And factor 10A gets trapped in the complex and it remains active. And heparin cannot target them. Likewise, heparin cannot inhibit thrombin that is actually bound to the clot. So when a clot forms, thrombin actually gets captured into the clot. Heparin cannot really inhibit that. So when the clot dissolves, thrombin can be released and that can restart new clot. Heparin cannot target because heparin is not able to target thrombin bound to fibrin. You might have recurrent thrombosis that might happen. So heparin has a number of different problems, and yet we are using heparin for more than 100 years, or more than 90 years now. Okay? And likewise, you can actually have osteoporosis, things of that sort. And all of this is primarily because of the negative charge of heparin. Actually, too much negative charge of heparin. What is heparin-induced thrombocytopenia? Very quickly, heparin-induced thrombocytopenia refers to loss of thrombocytes. Thrombocytes essentially means platelets. When the platelet proportion goes down significantly, such as 50%, then we say, such as 20 to 50%, then we say it is thrombocytopenia, and heparin induces it. It typically starts 4 to 14 days after the start of heparin therapy and arises because the patients develop antibodies against a complex that is formed in blood. This complex is unfractionated heparin binding to platelet factor 4. Platelet factor 4 can actually be released by platelets. In the process of activation, of platelet activation, platelet factor 4 can be released and heparin binds to it, and it generates an antigenic reaction, and therefore it induces antibodies. These antibodies start chewing up platelets, or actually eating away, clearing platelets, which reduces the concentration of platelets in blood. But it also activates platelets, and activated platelets can form a clot. So why did we use heparin in the first place? To inhibit clot formation. What are we getting? Some patients are getting thrombocytopenia. What is happening in there? Platelets are getting more activated, and therefore you get a clot. So what was being used to prevent clot formation is actually giving you clot formation, and that's a major problem. It turns out that this effect is generally observed with unfractionated heparin, much less with low molecular weight heparins, and essentially nil with pentasaccharide. So as the chain length decreases, the thrombocytopenic effect decreases. Okay, is that clear? Yeah? All right. How is heparin not able to inhibit thrombin in the fibrin-bound form? It turns out this is thrombin. Okay? Thrombin has an exocyte which is called heparin binding exocyte, or exocyte 2. Remember, I showed you that thrombin also binds and it captures, and you have a bridging mechanism. So this is that site in more detail. Fibrin also binds here. Okay, so fibrin's chain, especially the gamma prime chain of fibrinogen, binds in the same site as heparin, and therefore both of those overlap. So in fibrin, you have the gamma prime chain already bound to thrombin. So heparin cannot bind to thrombin. Because heparin cannot bind to thrombin, it cannot inhibit it. As simple as that. Okay. I'm telling you a lot of fundamental things. I hope you are able to understand it. Am I going too quickly? No? You feel fine? All right, because we have a lot to cover in this 50 minutes. Okay, so now we are going to the topic of low molecular weight heparins. Once again, this is a fascinating topic. What have we learned so far? Heparin is a mixture. Heparin is a polymer. Within that, the 5 residue sequence is the one that is the most active sequence, right? It binds to antithrombin. The longer chain and higher negative charge induce adverse effects. So what would be the simplest thing to do? Simplest thing would be to chop it, to bring down the length to smaller fragments. Of course, the pentasaccharide that we discussed is very difficult to produce. This is at the time where the pentasaccharide was not available. Now the pentasaccharide is available. But back in 1990s, fondaparinux was not available. Fondaparinux was introduced in 2001. So in 1990s, simple idea came up. Hey, how about just chopping heparin into smaller fragments? And so pharmaceutical companies basically started chopping heparin such that a typical chain of heparin, which has an average molecular weight of 13 to 15,000, is typically cut twice, and you generate a chain of approximately 5,000, 3 to 5,000. That chain is called low molecular weight heparin. Okay? So basically you need to have 2 nicks in an average chain of heparin. And you would get low molecular weight heparin. This was a major area of research. Why? Because heparin is a product that's been going on, has been used for a very, very long period of time. And there are a number of ways in which you can break down the chain of heparin. Number of ways. So every pharmaceutical company would be able to generate new method of preparing low molecular weight heparin. Some of them used an oxidative procedure. Some of them used an eliminative procedure. Some of them used a deaminative procedure. Different methods. Even today, there are papers in 2018, 2019. Papers are being published in very good journals where newer depolymerization methods, such as light, okay, such as gamma radiation, is used to cleave heparin and generate low molecular weight heparin. But you realize what is the value of this? The value of this is that if you have a newer method, you'll probably get a new structure, right? And if you get a new structure, you have intellectual property. So now you can make money, right? As simple as that. So basically, we are generating low molecular weight heparins, but the low molecular weight heparins are now going to have different structures. Okay, so start paying attention, close attention to what is happening in the field. Okay, yeah. So these are the typical methods that are employed by pharmaceutical companies. Okay. Obviously, we have to use unfractionated heparin because low molecular weight heparins have to generate from unfractionated heparin, right? So we use pig intestine. Today we use pig intestine, and we have to purify that. Okay, stage 12, minimally stage 12, and then as of now, the ones that have clinically succeeded utilize these 3 methods. As I told you, there are more methods than these, but they have not succeeded clinically. Oxidative method uses hydrogen peroxide. Once again, heparin is cheap. Okay, it's becoming more expensive, but it's inexpensive, and which is the reason why it continues to be used even today. So we now have to come up with low molecular weight heparins that are relatively inexpensive. So we cannot use really sophisticated reagents. So all of these reagents are fairly easy to produce. So oxidative method uses peroxide, hydrogen peroxide, and you get a molecule called paraperin, which is also called fluxer. This is not available in the United States. It's available in Europe. Or you can do the same thing with cuprous ions, and that is called arteperin or normiflow. Once again, it's available in the United States. Basically, what is happening is the peroxide or the cuprous ion generates radicals. And these radicals, if you simply use the concentration well, these radicals induce cleavage in the molecule. Very quickly, we don't really have a whole lot of time. Deaminative depolymerization uses nitrous acid. Okay? This uses nitrous acid. What are the low molecular weight heparins that have been generated? Darteperin is available in the United States. It's actually called fragment, or nadroperin, or reviperin. These are available in Europe. Or it could be isoamyl nitrite, which is another version of nitrous acid, essentially similar thing. Okay. And basically, what this does is nitrous acid removes an amine from glucosamine. and it cleaves the glycosidic bond, interglycosidic bond. Beta eliminative depolymerization uses elimination. Okay? It uses elimination reaction. And you can use two different approaches here. You can use heparinase, which is an enzyme that cleaves heparin. And that is enzaparin or inoheparin. This is available in the United States. Or you can use sodium hydroxide. And that is called enoxaparin or Lovenox. Enoxaparin is available in the United States. So in the US, 3 low molecular weight heparins are available, clinically used. Dalteparin, enzaparin, and enoxaparin. These are the trade names. These are the generic names. The trade names are Lovenox, Inohep, and Fragmin. Okay. Enoxaparin has captured 80 to 90% of the market. The rest are laggards following behind. Okay? Now, elimination introduces a double bond on the uronic acid side. So you get a UV chromophore in the mouth. And obviously you get so many other things. But basically, I mean, there's a lot of information here. I don't want to cover everything. You can read. But basically, what has happened? What do you read from here? You read from here that you can take an old technology, do a little bit of modification, and generate completely new molecules and get 20 years of patent life. Right? And you can make a whole lot of money. Which is why a lot of companies were behind the process of developing low molecular weight heparins. Remember, this is 1990s. Okay? If I ask you a very simple question, if you start with unfractionated heparin and you use any of these molecules, any of these conditions, what kind of product will you get? Will it be homogeneous or will it be heterogeneous? It will be heterogeneous. This is 1990s, right? Where the FDA was there, where the FDA essentially said that chiral drugs have to be chirally pure. How many chiral centers are present in every sugar unit of heparin? Well, 5 positions are chiral in every monomer. And if you consider the pentasaccharide, how many chiral centers are there? Lots of chiral centers. This is 1990s. This is completely heterogeneous. Do we know the structure of any of these low molecular weight heparins? No. And yet, all of these got approved. Okay? How were they approved? This is the structural characterization of a molecule that was approved by FDA in 1995. Okay? This is an example of heparin, and this is the lead. Okay, so this is what company said, which is Sandoz. Sandoz essentially said, enoxaparin has this structure, and please approve use of this molecule. What is enoxaparin? The average molecular weight is $4,500. It's not 4,500. It is an average molecular weight. Okay? The polydispersity is 1.1 to 1.5. What kind of a range is it? It's a 50% error in polydispersity. Right? If you do an experiment and you say I have an error of 30%, your professor will say, that's not good experiment. Look what is here. What types of chains constitute low molecular weight heparin? You could have a disaccharide, or you could have 32 monomers. The chains can be anywhere from disaccharide to 32 monomers. Hexadisaccharide. Disaccharide to hexadisaccharide. Within this, the proportion of chains is less than 2,000 constitute 20% of chains. Between 2000 and 8000 constitute 68% of chains. And chains greater than 8,000 constitute less than 18% of chains. Okay? These chains have a characteristic fingerprint in a particular technique called capillary electrophoresis, or LC, liquid chromatography. And they constitute 70 to 80%. Okay? Not only that, although we keep saying that these are disaccharides, but some of the chains are actually not disaccharide. They might be trisaccharide. They might be pentasaccharide. Okay. And then they have a statement saying that you may have chains that are uncharacterized, that we don't know the structure at all. They identified a specific proportion of 8 known disaccharides, X proportion of each of those 9 disaccharides. The high affinity pentasaccharide sequence is now reduced from 1/3 to approximately 1/4. So you've actually gone down. You have eliminated few high affinity pentasaccharide structures. And then in the preparation, in the synthesis of low molecular weight heparins, you have introduced sugars that are not naturally present, such as galacturonic acid. So you have glucuronic acid and iburonic acid. But this one, galacturonic acid. But enoxaparin has galacturonic acid. What is the proportion of this new monomer? We don't really know. It's unknown. You can have 70%, reducing N is 70% glucosamine, 30% is a new type of glucosamine called manosamine, which is not present in nature. And then you have 1,6-N-hydro ring structures in enoxaparin of approximately 15 to 25%, which are also not present in nature. So basically, Sandoz essentially said, this is the structure of enoxaparin, in which this particular entity, which has nothing to do with biological activity, it is simply there because it was generated in the reaction, that it said that if somebody wanted to make a generic enoxaparin, they have to demonstrate that they have a structure which has nothing to do with biological activity. 1,6-N-hydro ring structure. And therefore, there was a lot of litigation that was going on that essentially prevented generic makers from introducing the product into the clinic. And Sandoz this is 1,6-N-hydro structure. This is the 1,6-N-hydro part. This is manosamine, and this is the unsaturated thing. So these are the 4 non-natural structures that are present in low molecular weight heparin called enoxaparin. Is that clear? Yeah? Okay, I'm going to skip this part because this is simply a repeat of so many things that we have already discussed. Okay, so why are we discussing this concept so much? If I ask you the question, can anybody, if for example somebody came up with a new product which was homogeneous and it ran through the patent life, and somebody else said, I want to make this product, and they develop a method, they simply have to match the structure and say, we have a generic version, right? Can anybody make generic enoxaparin if this is the structural characterization? What would be your first guess? Your first guess would be, this is nearly impossible to make, right? This is nearly impossible because there is stuff in here that is not present in nature. The process of obtaining this molecule is trademark secret, theoretically. Right? We don't even know what temperature conditions and things of that they use, what concentration that they use, because companies tend to protect it. You had to have odd and even chains. You had to match this proportion. And then finally, you had to come up with some useless structure which has nothing to do with biological activity and match that. And if you don't get that match, basically you fail. Because it's not that your molecule is non-active, it's not matching the trademark product. If you don't match the trademark product, you're basically toast. So, for a long time, people didn't even try. But obviously, there were some stalwarts who actually tried. And today, 2 generic enoxaparin are used in the clinic. Okay, one company is from an MIT professor, and the other company is Teva. No, not Teva. Teva failed. Is Amphastar. And by the way, the 2 generic manufacturers of enoxaparin fought with each other. So the fighting wasn't between the generic and the trademark. The fighting was between 2 generic manufacturers. So life is very complicated. Anyway, all of this became possible because of the rules that came into being because Congress applied, asked FDA to develop these rules. Those rules are called the rules of biosimilarity, and they come under a specific law that came into effect in 2009. Because of this fighting, and because the prices of enoxaparin and others kept high, that the patients were not really being served well. So Congress took this up, and they said, FDA, you need to develop rules so that other people can come up. So now we have biosimilarity rules that help with this entire process. And it is because of these rules, plus the persistence of these companies and hardworking individuals, that now we have generic low molecular weight heparins. Otherwise, this was essentially an impossible problem. So, biological molecules, heparins, low molecular weight heparins, come under the category of biological molecules. These are not really drugs. Drugs essentially are small molecules. These are biological molecules because they are fairly large and because of the way in which they are made, and they are isolated from nature. Even low molecular weight heparins, they are synthesized, but the original product is still an animal-derived product. So they're still biologicals. So that is why we don't use the term generic or biogeneric. We use the term biosimilar. They are not identical in structure. They are similar in structure. Okay? Now, let's skip all of these parts. So why do we need biosimilarity? Okay? We need biosimilarity because these are manufactured from biological factories, cells, animals, those kinds of things. It's very difficult to control conditions. Chemically, you can control conditions very well. But biologically, the cell lines might have changed, the passage number might have changed, the temperature will have an effect, the cations will have an effect, the buffer will have an effect, the state of everything around will have an effect. And therefore, what comes out of these cells, especially these kinds of molecules, unfractionated are different because these are dynamic entities. So therefore, we cannot really get the exact structure, exact composition all the time. So that is why we say it has to match the general profile, which is why all of that is defined. Molecular weight has to be this, approximately. This should be the range, 20% of this size, 50% of this size, things of that sort. An alternate manufacturer would definitely not have the original cells for that matter. Right? Nobody would like to share their cells. Right? Why would they? And then because of these, you might actually generate heterogeneity. Now, heterogeneity might not really have clinical variability. Just as I said, 1,6-N-hydro has nothing to do with biological activity. But it's there. So even if it's not there, you will have the same biological activity. What patients are interested in is same biological activity. Therefore, the FDA came up with these kinds of definitions, which ease the entire process. This is another reason why biosimilarity is important, because characterization of these molecules is extremely complicated, And even today, it's very difficult to characterize heparin or unfractionated heparin for that matter. So the law that came into fact was the Biologics Price Competition and Innovation Act of 2009. And under these, there were rules that came into being so that biosimilars could be approved. And the essence of this rule was you should have a side-by-side comparison. So you should always have a trademark. You can never have de novo, right? So if you come up with a product, it's a biological product, there's no question about biosimilarity because it is de novo, completely new. But if you have a trademark, then you can come up with a biosimilar by side-by-side comparison. Then the rule is that you might actually get away with fewer patients. In clinical trials, you have to use patients. Okay? But if you already are comparing, and the comparison is almost equivalent, then you can get away with fewer patients, which means the cost to produce biosimilars will go down. It turns out that biosimilars may be approved for fewer indications. So the trademark product might be approved for 5 indications. Thrombosis, okay, stroke, okay, edema, things of that sort. But the biosimilar product might be only approved for stroke. That's it. Why? Because that comparison was done in clinical trials, even with fewer patients. If you don't do that with everything, then it might be approved for fewer indications. And you have to ensure that the toxicity, especially the immunogenicity differences, are of no significant value. Okay? Differences are of no significant value. Interestingly, you would be surprised to find that if the generic product, the biosimilar product, is having lower toxicity than the trademark product, it is not considered as a biosimilar. You cannot improve on the original product. You have to show that it is exactly the same and no more. It can definitely not be worse, but it cannot be better. Got it? That's the rule. Okay. So the question is, are these low molecular weight heparins biosimilar? Is carnaprin, fluxum, fragmin, have biosimilar? How many say yes? No. Okay, only one. How many say no? Why? What's that?
That's a lucky guess.
Lucky guess. Oh, okay. Well, these are not similar at all. Because these are the trademark products. Remember, biosimilar means you have to have a trademark. You have to have an original product. These are all original products. So therefore, generic enoxaparin is a biosimilar product. But there is no generic low molecular weight heparin. There can never be generic low molecular weight heparin. You can have generic dalteparin. You can. It has not yet been produced. You can. But you cannot have dalteparin as a generic for carnaprin. Because those are completely independent. They are made differently. Things are completely different. Okay? Now, I know this is getting too complicated for you all, but basically there are 5 criteria that are used to establish biosimilarity. Okay? You have to evaluate similarity in differences, physicochemical properties. Sorry, this is not one of them. This is the first one. Physicochemical characteristics. What is the source of unfractionated heparin? Okay? Notice, a biosimilar product, low molecular weight heparin, has to have the same source as the trademark low molecular weight heparin. You realize the implications of this? If I always give this example, if you were to go and say, I want aspirin, you go to CVS and you purchase aspirin from CVS. You ask the question whether this came from the original Bayer. You never. But here, the FDA is basically saying that if I make generic enoxaparin today and try to put it to the clinic, I have to use the same unfractionated heparin as Sandoz is using today. So I have to use the same unfractionated. That's phenomenally complicated, right? That means I have to go and find that manufacturer in China and purchase it from him. Obviously, structural composition, in vitro biological activity, in vivo pharmacodynamic profile, but this is one important source, one important criteria. And then you have to match all of these criteria in order to generate. And as I told you, Momenta, which is a company from MIT or in Boston, and Amphastar, they are selling 2 generic low molecular weight enoxaparin currently in the clinic. And by the way, they are making a lot of money, although it's generic. Okay? So I hope you enjoyed this, primarily from the perspective of how science progresses, and also tells you a little bit about what is the state of sort of drugs with regard to heparins today. Despite the advances, we are still essentially in the dark ages. Okay, any questions? No? All right, let's stop here. Next week we are going to have presentations. Okay? And as I said, if you have any questions, let me know.
Thank you.
Sure. Christina, can you turn it off?
Just on that point. If you want to keep it as a precious
I
here.
really